Hey guys, welcome back. So this is gonna be a little different. Instead of writing about seminar, I talk about physics, and then I'll continue doing other math topics in the future. So this is 2020 2013 Physics C Mechanics of Archaea and Drag, because that's the concept we were learning in class today. So yeah, we'll just go through this problem, okay? So it says that a box of mass m initially at rest is acted upon by a constant applied force of magnitude Fa. We can see that here, as shown in the figure above. The friction between the box and the horizontal surface can be assumed to be negligible, but the box is subject to a drag force of magnitude Kv, or V is the speed of the box and K is a positive constant. Express all your answers in terms of the given quantities and from the fundamental concepts. So that's a pretty simple problem. And then they're asking to draw and label the forces, not components. Um, what that means is that let's say you have a ramp, right? And then something like that, not perfect, and then you have object here. So we know that there's going to be weight downwards of mg and a normal force perpendicular to the surface. And when it's talking about components, it's going to be talking about the force that's going to move this object down the ramp, which is going to be mg sine theta. And in this case, we don't include that. We're just talking about forces that directly act on the object. So, in the free body diagram here, the object is represented by a dot, so this is m, right? And then so the forces we're going to have is definitely Fa in the positive direction. I think we can set a coordinate system, right? X positive and then Y positive, right? Um, we have mg downwards, force of the normal force top, and then we're gonna have the drag force of kv. Actually, I think I should draw this a little less. So kv. Yeah, and that's it for part A. All the forces are labeled, and yeah, we can move in. So part B says, write but did not solve a differential equation that could be used to determine the speed of v of the box as a function of time t. Um, okay, so I think I'll go off to the side actually, over here, and then we know that the net force of an object is equal to mass times acceleration. Um, so in this case, our net force, is gonna be the forward force of Fa minus the the drag force, right? And then that's equal to ma. Now, when they say to write but not solve a differential equation, another way to display acceleration in calculus terms would be a is equal to dv dt, which is just taking the derivative of velocity, uh, the velocity function. So basically what this is going to be is, okay, you have f a minus kv is equal to m dv dt, and that's for part B, and that's it. That's it for part B, because we've written but not solved the differential equation. Yeah. Now it says to determine the magnitude of the terminal velocity of the box. So terminal velocity means it's at a point when an object is dropped, where you're, let's say this is an object, let's say a ball, right? Let's say when the ball is dropped, after some time, the force downwards of mg will equal the drag force upward. Let's say kv in this case. So there's going to be a point that the force downwards is going to equal the drag force, which is what it's talking about in part C, to determine the terminal velocity. So all you need to do for this is say, okay, the force forward is equal to the drag force. So Fa equals kv, and then I'm going to add a subscript on my v to show that it's the terminal velocity. And now you just solve for terminal velocity. So we're just going to divide both sides by a k. So we're going to get f. Okay, never mind. F of f sub a divided by k is equal to terminal velocity. That's not time. That's just the subscript for velocity. Okay. Now, part D says to use the differential equation from part B. So this one. And to solve for the equation for the velocity as a function of time, assume that v is equal to 0 at time of t. So those are going to be our bounds when we do our integrals, and it's really important to have that down. Okay. Okay. So part D. So part D, I'm gonna rewrite that equation I had earlier, which is gonna be f sub a minus kv is equal to m dv dt. So from here, what I'm gonna do is I'll move the dt on the other side and divide by m. So basically what I'll have is dt over m is equal to dv over f sub a minus kv. So what I did is I isolated all the terms that have v on one side with the dv, v, make sure that looks like a v, and all the terms that do not on the other side, which includes the dt and the m. So now what we're going to do is now we're going to take the integral of both sides. So this one's going to be from 0 to t, and this one is going to be from 0 to v, as it says on top. So those are our bounds. And then if you integrate this is just going to be t over m, and that's going to be equal to, so we can do, so actually we can take the 1 over my negative k, because that's the constant. So if you were to do a u substitution, right, since this term does not have since f sub a does not have the v variable attached to it, if you were to differentiate this part, this would just go to 0. So we just have, okay, so I should do that actually. Let u equal f a minus kv. So if I were to do dv du, this would just go to 0 minus k, right, which is just negative k. And if I were to solve for du, this would just become 1 over negative k, right? And then I can just sub that back, and since this is a constant term, I can take that out of the integral sign, which would just be negative 1 over k. And when we do take the integral of this, we're going to have a natural log term, so which is going to be natural log of f sub a minus kv, and our bounds from 0 to v. Yeah, and now we just use the properties of logarithm, and we resolve this integral. So we're going to have tm divided by m. Actually, I can just move the k to the other side, so I have negative k tm. And that's going to be equal to my natural log of, so if I were to plug in the upper bound v into this equation, I would just have natural log of f sub a minus kv, minus, if I were to plug in 0 in this side, I would just have fa. So I'd have natural log of fa. And then recalling back to logarithm rules, if you're subtracting two logarithms and natural logs, you're essentially dividing them. So if I'll have negative kt over m is equal to natural log of f a minus kv over fa. Now since we have a monomial in the denominator, like a single term, we can actually break the fraction up a little bit. So we can say, okay, negative kt is equal to m. I mean negative kt divided by m is equal to natural log of, that's f divided by fa minus kv over fa. This would just become 1, and then we can simplify to negative kt natural log of 1 minus kv over fa. And now we can raise this side to the e power to remove the logarithm, and we can just have e, that's a terrible e, okay, e to the negative kt over m is equal to 1 minus kv over f sub a. And from here on out, you're just starting to isolate for v, which is ultimately going to end up being adding, right? So it's going to be e to the negative 1 plus e to the negative kt over m is equal to negative kv over f sub a. Now, what I can do is I can divide both sides by the negative 1, which would just give me the positive versions of this 1 minus e to the negative kt over m is equal to now kv over f sub a. And then I can just multiply by the reciprocal, which is going to be v is equal to, I'll have, okay, 1 minus e to the negative kt over m multiplied by f sub a over k, and that's part D. So it's a little bit long, but I think following it step by step will ensure that you don't make any mistakes in this type of problem, especially because the steps are kind of long and it's kind of easy to make mistakes, so I prefer to follow a methodological approach to it. So yeah, that's part D. Now, I think there's like one more part. Yep. Okay. It's asking to sketch a graph of the speed v as a function of time. Okay, so we know that an object, as it falls, initially it's not going to have terminal velocity, but at one point it will have terminal velocity until it uh, makes contact with something. In this case, maybe the ground, or just stops, becomes stationary. So what's essentially going to happen is that we're going to have in our vt axis, this is going to be a terminal velocity at one point, at some point. It doesn't have to be exactly accurate, but it has to be at some point, not zero. So if you look back, we know that's our terminal velocity. So it's f sub a divided by k. So we're going to have f sub a divided by k, and I'm going to draw a little dashed line right there to indicate that's where we're kind of going to have kind of like an asymptote there, where, yeah, because it's an exponential graph. We know that at t equals 0, our function is just going to be, so that's what, e to the negative kt, but if it's 0 divided by m, that's just going to equal 0. So we know that at time equals 0, we're going to be right here, which also makes sense because our velocity is also 0. And from there essentially, as you approach infinity, we're going to get fa over k. This is our terminal velocity. And when you have 1 minus, okay, e to the negative kt divided by m, and as you approach infinity, as you tend to infinity, this would approach fa over k. And if we were to graph that, that would end up looking something like this. So, okay. Something like that. It looks like a curve. I mean, exponential curve. So yeah, something like that. Okay, I hope that was helpful. Yeah, thanks for watching.